So good morning. Welcome to Mass 814, Algebraic Theory of Semigroups. So this is the first lecture of the course. So as I said, the title is Algebraic Theory of Semigroups. We are going to be talking about semigroups. We will be following this material, that is the textbook, Fundamentals of Semigroup Theory by John M. Howe. This will be our reference material for the course. And then we are going to cover the first three chapters of the course. The chapter 1 is introductory ideas, and then the second chapter will discuss the concept of Green's relations, and the third chapter is talking about zero simple semigroups. And then, if time permits, we are going to add an extra chapter to talk about transformation semigroups in general. So this is what we are going to cover in this course. And Fundamentals of Semigroup Theory by John M. Howe will be our reference material. Well, there are other textbooks in semigroup theory, like the Algebraic Theory of Semigroups by Clifford and Preston. There are 2 volumes book written by Clifford and Preston. They were much earlier than this book, Fundamentals of Semigroups. This book was published in 1995, while the other books were published in 1960, 62 and 67, the 2 volumes. So semigroup theory is much a younger area of algebra than group theory and ring theory. Actually, in fact, before the 20th century, there were consideration of semigroups arising from looking at binary relations and also transformations, they said. But then there was also the work of Cayley and Jordan and many other mathematicians looking at transformation groups, that is, group of permutations. But then that was the beginning, initial motivation to studying transformation semigroups. In the 20th century, we had the contribution of A.K. Anton K. Soshkewicz and John von Neumann, working, who initiated the algebraic study of semigroups, the structural study of weaker algebraic structures that are not group. Group is to satisfy 4 properties, 4 axioms, but then semigroup is just 2 axioms. So, but then they realized that there are other algebraic objects that do not satisfy, they do not qualify to be groups, but they are semigroups. They satisfy closure and associativity. And then Soshkewicz also published some work which is the beginning of systematic study of simple semigroups. We will define what simple semigroup is in this course. And then later on in the 1930s and the 1950s, von Neumann in 1937 introduced the concept of regular semigroups. But while working with operator algebras, he was working from analysis perspective, looking at operators between spaces like Hilbert spaces or Banach spaces, and then the collection of these operators, if you are to study it as a whole with respect to the binary operation of composition of the operators, it's actually a structure which is a semigroup. And then there he introduced the notion of, he was looking at that thing, like he was calling them ring of operators. But inside that ring, the multiplication is a semigroup with respect to multiplication. And then he introduced the notion of regularity, that is an element being regular and also the entire structure being regular when everything is regular. 1940s and 1950s, there were also the contribution of Clifford and Pristin formalizing the theory of semigroups, where Clifford studied idempotent and their role in the structural theory of semigroups. But then 1961 and 67, they published 2 volumes. Okay, I mentioned the first volume was published in 1961 of the Algebraic theory of semigroups by Clifford and Pristin. And then that was a golden age because semigroup theory now has started being recognized as an independent area of study, distinct from groups. And then connections with other areas of mathematics started to emerge, like connection of semigroup theory with automata theory. These were initiated by the mathematicians like Schellenberger, and then connecting semigroup theory to formal languages, automata. And then there were applications and also logic, computer science. In fact, there was how he said, if one is to ask in one of his papers, if one is to ask for an ideal syllabus of computer science, it must to contain some element of semigroup theory. You would not see group theory or ring in that syllabus, but semigroup theory must be there. Just to show you how important semigroup theory is in the aspect of computer science, automata, and so on. And then later on, there was a study of issues like topological semigroups. Looking at semigroups where the underlying set is a topological space or metric spaces and so on. And then operator algebras, like I mentioned, Van Neumann was studying from that perspective of looking at operators between norm spaces. So there were connection to functional analysis of semigroup theory, but most of that is mostly called topological aspect of the semigroup. But then what we are going to be talking about is semigroup, the algebraic theory of semigroup. So looking at it only from the algebraic perspective, so this is what we will be doing. So like I mentioned, we are going to look at chapter 1, 2, and 3 of the book Fundamentals of Semigroup Theory by John N. Howe. So I'm starting from the very beginning by defining what a semigroup is. So actually, we start with the definition of what a semigroup is. So a semigroup is a non-empty set S. So you should take note, the set has to be non-empty, and then together with an associated binary operation. Defined on S. That is what we call a semigroup. Once you have a set non-empty, and there is a binary operation. What do we call binary operation? Defined on S. That is a rule of combining two elements of S to produce a new element of S. So it's a mapping from S cross S. So a binary operation is actually a map from S cross S to S. So it takes a pair of elements and sends it to what? An element. And mostly we denote the result of combining X and Y by XY. So we just use juxtaposition or concatenation. So we donate multiplicatively. The binary operation is most often donated is usually donated multiplicatively. Well, so it means if we say the binary operation is associative, it means we are saying for all x, y in z in S, we have a way of combining x, y to produce a new element in the semigroup, but then we require the combination rule to be associative, meaning x, y, z should be equal to x, y, z. So if you combine, it doesn't matter how you combine elements. I hope it's okay. So, which means you can do away with the bracket while working in a semigroup. I hope it's okay. You don't have to care about putting brackets to know which group of element to combine before combining the others. I hope it's okay. That is the advantage of having associativity. So you can combine anyhow. If I have a long product, I can just look at the center and combine anyhow. So that is what the binary operation is doing. So if in a semigroup S, we have that for all xy in S, xy is equal to yx, then S is called a commutative semigroup. Sometimes the word abelian is used. It's not very common, or abelian semigroup, because we use abelian mostly for group. But then the word commutative semigroup is okay. Yeah. So if the operation is commutative, then you call it a commutative semigroup. We know what commutativity is. It means like when you are adding numbers, you say 2 plus 3 is the same thing as 3 plus 2. So that is commutativity. If a semigroup S has an element say 1 with the property that for all x in S, x times 1 is equal to 1 times x, this is 1, is equal to x. Then the semigroup is called a monoid. Yes. Or you say a semigroup with identity. Or a semigroup. Maybe I should define the element first. Then the element 1 is called an identity element of the semigroup. An identity, or simply identity of S. And S in this case is called a monoid. Or a semigroup with identity. So a monoid, or you can say a semigroup with identity. But any element in a semigroup doing this is called a semigroup with identity. It's called the identity element of the semigroup. As the concept of identity is very clear to us, I think we don't need to waste much time there. Yeah, yeah, it has to be a semigroup in the first instance before it's qualified to be in a monoid. So a monoid requires two properties or three, because you say a semigroup is a set with a binary operation, an associative binary operation. Then, if in addition to the associativity of the binary operation, you have an identity element, then you have a monoid. Semigroup is a monoid. So every monoid is a semigroup, but not conversely. There are semigroups that are not monoid. We don't have the presence of identity in such semigroups. Yeah, semigroup is more general. Like if you are looking into the universe of all semigroups, all monoids will be found in there. But then there are semigroups that are not monoid. So if you are looking into the universe of monoid, so many semigroups will not be present there. So in that sense, you say semigroup is more general. All right. So an element 0 in a semigroup, I want to define 0 element. In a semigroup S with more than one element. So we want the semigroup to have more than one element, or with at least two elements. I should say with at least two elements. The semigroup S with at least two elements is called a 0 element of S. It's called a 0 element of S if for all x in S, 0 times x is equal to x times 0, and that is equal to 0. So an element for which whenever you multiply with every other element, you still get the element back. It's called 0. This is what we know of 0, even in numbers. We know what 0 is. 0 is an element that if you multiply with every other element, you get the 0 back. So such type of element are called 0 element in a semigroup. And in this case, the semigroup will be called what? A semigroup with 0. The semigroup S is called a semigroup with 0. If you say a semigroup with 0, you mean a semigroup in which there is the presence of 0 elements. Okay, don't worry, I'll give you examples of all this. Okay? But before giving you example, let me just prove the fact that this 0 and this identity cannot have more than one of them. Okay? So if the identity and the 0 element of a semigroup are unique, whenever they exist. So if there is this identity element in a semigroup, it must be unique. If you have a 0 element in a semigroup, that 0 element must be unique. Meaning what? A semigroup cannot contain two different identities. of two different zero elements. So, and this will not be difficult to see. For we mostly do this by contradiction. You take two different identities and you see that they cannot be different, they must be the same. Because if you try to identify any two identities, if one and the one prime are two identities, for S, for a semigroup S, then you immediately see that one prime can be written as 1 times what? 1 prime. Well, yeah, because 1 is an identity. So if you multiply identity times some element, you will still get the element back. So since 1 is identity, this is giving us 1 prime. But then 1 prime is identity. So if I multiply 1 with 1 prime, I still get what? 1. So this is immediate. I hope it's okay. In fact, there is almost nothing to worry about, nothing to write down. Okay. Similarly, if you have any two different zeros, the same thing. That is, if 0 and 0 prime are taken to be different zeros, then the 0 prime will be 0 times 0 prime. Why? Because 0 prime is a 0. So if you multiply with any element, you get the 0 prime back. And 0 is also 0. If you multiply with anything in this semigroup, you still get 0. So the same thing. I hope it's okay. So actually, this is it is immediate from the very definition of this identity and the 0 that these things are unique. And that is the reason why we can say 1 is the 0, is the identity of the semigroup, and 0 is the 0 of the semigroup, because there is only one of it. I hope it's okay. So this is the notation. Okay, let me give you examples of semigroup. I have just been saying semigroup, just without giving any example. I am sure you must have some examples already in your mind. So, examples. My example number 1 is to take which set is the set of natural numbers with addition. It's a semigroup. So if you take natural numbers, what do you take to be the set of natural numbers? 1, 2, 3, and so on. You know, the counting numbers. Okay. So if you take this together with addition, because it's not only a set that is a semigroup, it has to be with a binary operation. So if you take together with addition, it's actually a pair, you know. But I will always say S a semigroup. To me, the binary operation is implicitly understood inside, and it is donated multiplicatively. So if you take the binary operation on the semigroup, on the set n of natural numbers to be addition, this is a semigroup, because we know that this is associative. To add numbers like this is associative. I hope it's okay. And it's closed. Yeah, it's a binary operation. That is what closure means, to say that it is a binary operation. Associativity is also understood to us. Likewise, if you take n with multiplication, it's also a semigroup. And also, if you take z with addition, you can take the set of integers. Integers will be what? The natural numbers 1, 2, 3, 0, and the negatives. So if you take with multiplication, this is a semigroup. Likewise, if you take with what? Integers with addition is a semigroup. Do you get it? Okay. Well, this semigroup. Well, I can take the set of natural numbers, but this time around, I want to see the natural numbers from include 0 to be among the natural numbers, like this, and then I take with addition. Okay. So you see this set, this semigroup, Does it have identity? There is no identity here. I hope it's okay. Yeah. Even though 1 is there, so don't get confused by our notation at this point. When I am writing 1, I have not even pronounced what is the nature of element of S. Nobody said what are the elements in S. It can be matrices, it can be anything. Are you following? So the fact that I'm saying 1 is the identity here doesn't mean 1 the number 1. I hope it's okay. If there are matrices, then it is 1 represent identity matrix. If there are mappings here, 1 is representing the identity map. I hope it's okay. So when you write 1, don't get confused by the notation. Okay. So the fact that you are seeing 1 element here, it's not enough to conclude that there is identity, and you now declare 1 to be the identity. You have to refer to the binary operation. Okay. Identity means that element of which, if you multiply with any other element, you get what's the element back. And here you don't say multiply, we say if we add. I hope it's okay, so we don't get that element. But look at this semigroup. This is a semigroup also, because clause is associative. This one has identity. And what is the identity here? The number 0. So this 0 is not talking about the 0 element. We are not, even when we write the 0 element in general as 0, we are not saying number 0. I hope it's okay. So it's the element that that possess the property we labeled as what? 0. It's just a label for the element. We write as 0. So, but now here the identity of this semigroup is 0, because our operation is addition. This is semigroup is identity, and the identity is 0. And this semigroup, it has identity. The identity is what? The number 1. I hope it's okay. There is identity also here. What is the identity? The number 1. Does it have 0? Yeah, the number 0, the 0 element of the semigroup, because operation is multiplication. So you see, this set was not a semigroup with 0 under addition, but with respect to multiplication, it becomes a semigroup. No, it wasn't with identity, so it was not a monoid, but here is a monoid. So changing the binary operation can make a semigroup that was not a monoid to now be a monoid. Are you following? So a semigroup structure is actually depending on the binary operation. It's the binary operation that mostly determines the structure of the semigroup. I hope it's okay. So you don't just look at the set and say, yeah, this is always so semigroup or not. No, with respect to the binary operation. And here is a semigroup. Does it have 0? 0 element is here. There is no 0 element here. But it has identity, it's a monoid. Now it's okay. 0 number, the number 0 is the identity. But there is no 0 element. You don't have that element that you add and always get the element back. I hope it's okay. So such thing does not exist here. So it was a semigroup with 0 under multiplication, but now there is no 0 with addition. Even though it was still a monoid, but here it's also a monoid. When you change from addition to multiplication, something is lost. The 0 element is no longer there. I hope it's okay. Okay? So you can take more examples. So the 6th example is to say all groups are semigroups. Yeah, simply because what? In fact, they are semigroup with identities. They are monoid with identity, because there is always identity in a group. So a group is always a semigroup, and there is also identity because it was already a group. Remember the axioms of group, the closure associativity, existence of identity, existence of inverses for every element, as in group inverse. We will still see semigroup with inverses, but we are going to modify the definition of inverse just slightly, kind to generalize it. Okay, so the notion of inverse in semigroup will just differ slightly than that of inverse in group. All right. Number 7, all rings are semigroups with respect to both addition and multiplication of the ring elements. Because with addition is already a group. We have just said every group is a semigroup. So with addition, every ring will still be a semigroup. And also with multiplication, you remember the axioms of ring. It should be closed and associative. That associativity is required. But then a ring may not necessarily have identity. If it is a ring with identity, then we have a monoid with respect to multiplication. I hope it's okay. In fact, that was what von Neumann was looking at, the ring of operators. And with respect to multiplication, it's a semigroup. It stops at the level of being a semigroup. It doesn't graduate to being a group. So that means that structure is worth studying. And it's all right. Number 8, we can take S to be the closed bounded interval 0, 1 and define multiplication of, so we define for all, let X be this, and define for all XY in S multiplication by minimum of X and Y. Then S is a monoid with 0. So identity will be 1 with 0. So it is a semigroup with 0, which is also a monoid. So it's a monoid with 0. The identity element is easily seen to be 1. In fact, you can easily check that this operation, taking minimum, is an associative binary operation. Because if you take 3 elements, if you take the minimum of A, X, and Y, and later on take the minimum of the resulting minimum with Z, the same thing as taking the minimum between Y and Z, and then taking the minimum of whatever the result is with X. So if you are taking minimum, you don't have to put order. You can just take minimum of 3 elements X, Y, Z. So associativity is immediate. So, and it's close because if you take minimum of the 2 sets already, of the 2 elements, they are already coming from the semigroup. Whatever the minimum turns out to be, it is already an element of the set of 0, 1. Are you following? So you can define like this on a closed bounded interval like this, and then you have a semigroup with a monoid with 0. What will be the 0 element? Yeah, it is the 0. Because if I take minimum with 0, always 0 is the minimum. Are you following? So the output of the product is always the element 0. And if you take minimum with 1, 1 is always greater than all the elements. So the output, if you take any element, X, and multiply with 1, you still get the element. I hope it's okay. So 1 is, because 1 is always greater, so the minimum will always turn out to be X if you do that. So this is, so in this semigroup, X times 0 will always be 0 times X and will be 0. And the X times 1 will always be 1 times X and would be X. So you have identity, you have a 0 in this semigroup. So, and if you have seen this, if you observe, with this given example, a semigroup can be of all sorts. It can be with 0, it can be without 0, it can be with identity or without identity. And you have semigroup with 0, there is no identity in there. You have semigroup with identity where 0 is not there. Are you following? So we have seen this. This is what all these examples are trying to repeat. In fact, you can do a slightly different one, taking S to be 0, 1, and then defining the product to be maximum of XY. This time around, you still get a semigroup. It's a monoid. So, if I may ask you, what is the zero element now? To be 1. Because if you take 1 and multiply with X, you are taking the maximum. And 1 is always maximum. Because 1 is coming from X is coming from here. So, and that is X times 1 always. So, anytime you multiply with 1, you get 1 as the output. I hope it's as the resulting value. So, 1 is the zero element. Are you following? Yeah. In fact, the reason why I'm giving you this example so that you should get clear with notations in algebra. They may be misleading sometimes. You see somebody writing 0 and you think he is thinking of the number 0 because you are already been familiar. You are familiar with 0. Always when you see 0, you think it is the number. So, but no. We are talking about 0 element, not necessarily the number. And in this semigroup, 0 is 1. Okay? And what happened with 0 times X? That would be X. And what happened with X times 0? It's still X. In fact, this semigroup is commutative. And all the semigroups I have considered here are commutative except here, this example, and this example. But every other example here is a commutative semigroup because here you can have groups that are not abelian, so they will not be abelian semigroup. And also here you may have rings that are not commutative, so in that situation. But don't worry, I will still look at some examples of semigroups later on. We are going to look at some fine example of semigroup that are not commutative. So this operation is already commutative. So, and you can see that if you do 0 times X, you always get X. So this situation, when you do 0 times 1 over 2, it is still 1 over 2. You know, and 1 over 2 times 0 will give you 1 over 2. So times here means taking maximum of the 2. And 1 over 2 is always greater than 0. So 0 is the identity in this semigroup. I hope this is clear. Okay then. So, so if you understand this, then we can now go ahead. So this lecture will be a lot of definitions actually, not too much proofs. So we'll be defining, because this is this introductory ideas and we say basic concept. So if a semigroup has no identity, because we will see later on in the theory that in many instances or many situations, when you are trying to analyze the structure of the semigroup or perform some analysis on a particular semigroup, you will require the presence of identity. So what if the identity is not there, present in the semigroup? If you discover that the semigroup doesn't have identity, you can easily adjoin it. So if you have a semigroup, if S is a semigroup that has no identity, we can adjoin an extra element. There is no identity here, so I will pick some element from anywhere, whatever, wherever it is coming from. Just pick an element not already present in the semigroup and label that element 1. So an extra element 1, this was not in S, and define. So since it wasn't coming from S, so binary operation is only defined in S. So you only know how to combine element of S, but you don't know how to do combination with this particular element you are bringing in. I hope it's okay. So what you do is to define For all x in S, the multiplication, you extend the product, you define 1 times x to be equal to x times 1 to be equal to x, and 1 times 1 to be equal to 1. Well, I don't mean 11 here. I mean 1 times 1. You know, my operation is being denoted by juxtaposition or concatenation. Just like
denote the binary operation with something like asterisk to avoid this confusion. I see that we just put x, y.
Yeah.
Try the operation to see if this way to avoid confusion.
You can do that, but it's not necessary.
For example, in the definition of group, we define a group to be G.
I understand what you mean. I should always write star y. Yeah, it's doable, but it's not necessary. It's an unnecessary effort. Why not just write xy? So, and you understand what you mean. Are you following? Because it consumes time to always put asterisk, and it also it's not necessary actually. So it's for simplicity of notation. You just write xy concatenation, because it doesn't harm you. There is no harm in doing that. So the only thing that is there is some chances of confusion. Maybe that is what you are trying to say. So, but try to train your mind into understanding that when you write things like this, if you are dealing with a semigroup, if the semigroup is of numbers and you say 2, 3, well, you should write a dot in between. This is just to distinguish between product of 2 and 3 and the number 23. Are you following? But if they are not numbers and you write x, y, you should understand it means x operation y. I hope it's okay. Yeah, I should have put some dots in between. Yeah. Okay. So if you put dot in between here, it's okay. You can do that if you so wish. Like here, you can say x dot 1 and so on. Yeah. Okay then. So we can easily extend the operation like this. And then see that with this extended version of the operation, and if you take 2 elements here, you already have a way of multiplying them. But any time it comes to multiplying with 1, you should behave like this. I hope it's okay. Then it is easily seen, then it is clear that S with this extra element that we are introducing is a semigroup. It's a monoid, not a semigroup. It's a monoid with this as identity. With the element 1 as the identity. So, what are we trying to do here? We are trying to say that even if there is no identity in the semigroup, you can always introduce the identity into the semigroup. This process is called adjoining. But when you adjoin, when you bring an extra element, you have to extend the binary operation to cover that element you have introduced. And this is what we have just done. So, which means it's always easy to introduce an element into the semigroup, a binary, identity element into the semigroup to get a monoid. So, and this is a very important uh, exercise. It means whenever I require identity, I can just bring it to come in. Okay? And this brings us to the definition of what we call monoid with identity adjoined, if necessary. So, for any semigroup, yes, we define S1 So given this semigroup, I can always get a new semigroup S1, which will now have identity to be equal to S. So S, if S has identity and S union 1 otherwise, that is in the situation where S has no identity. So we always do this. So in other words, S1 is just the semigroup already. If there is identity, so you don't need to do anything to it. But if there is no identity, you bring an extra element and do this kind of extension of the binary operation. And then the resulting semigroup is called what? A monoid with identity obtained from S or the monoid. I think because always you do this. The monoid obtained from S by adjoining identity if necessary. It's a very long name. The monoid obtained from S by adjoining identity if necessary. Yeah. So you can always get a semigroup with identity adjoined if necessary from a given semigroup. You are working with a semigroup and you realize that you need identity for some reason, you can always bring the identity and extend the binary operation to cover that identity. And you call the resulting monoid the monoid with identity obtained from S by adjoining S, obtained from S by adjoining identity if necessary. Okay? We can do a similar thing with the zero elements. If you don't have zero element, you can also introduce it by this adjoining. Okay? So similarly, if um, if S is a semigroup without zero, we can adjoin an extra element zero, and this zero we pick it not from inside S, just an extra element we bring from there. Okay, and define for all x in S 0 times x to be equal to x times 0 to be equal to 0, and when it comes to multiplying 0 by itself, we declare to be 0 also. So we have extended the binary operation to cover this extra element. Okay? Then it is then clearly this S with the extra element is a semigroup with 0. So we can always obtain a semigroup with 0 from a given semigroup where there is no 0. I hope it's okay. Is it possible to have 0 element in a group? Is it possible to have 0 element in a group? So I can define a similar notion of joining 0 to say that for any semigroup whatsoever S, we can define this symbol S to power 0 to be the semigroup S, if we have 0 already present in S, if S has 0, and to be S union 0, the extra we adjoin, which is now a semigroup with 0, so in the otherwise, okay? And what we do is to call this S1 a semigroup with 0 adjoining if necessary. So a semigroup with obtained from S, we should say it, obtained from S by adjoining 0, adjoining 0 if necessary. Why if necessary? Because of the way you define it. If there is 0 already, you don't need to do that, to adjoin. So it's not necessary to do the adjoinment. But if there is no 0, then that is when it is necessary to adjoin. Are you following? So the adjoinment is only when it is necessary that you do it. I hope it's okay. So this is what we call semigroup with 0 adjoin if necessary. Okay? As I ask you a question, do we have 0 element in a group? Is it possible? Can a group contain 0 element? No, yeah. I think that is the answer. Yeah, that is correct, Muhammad. I think it's not possible to have 0 element in a semigroup. I mean a group, because if it does, that element 0 will not have inverse. So you no longer have a group. If it has a 0 element, 0 times any other thing will always give you 0. So there is no any situation you multiply 0 with some element of the group to get identity. It's not possible. I hope it's okay. But let me make a remark here. While defining the 0 element of a group, you remember we said, I said an element 0 in a semigroup is at least 2 elements. So you want the semigroup, for a semigroup to contain 0, it must have at least 2 elements. This is what we said. Oh, why? That technical requirement, it's an extra technical requirement that the semigroup must contain at least 2 elements before you say it has 0 element. Because if you take a semigroup like this, consisting of only 1 element, so one thing you should understand is that the identity element and the 0 are always not equal. I hope it's okay. If the identity element and the 0 are always not equal. No, because if the 0 is to be also the identity, then you are saying it must satisfy this equation. 0x must be equal to 0 because it is the 0 element. And 0x must be equal to x because it is what? The identity element. I hope it's okay. But it's not possible for these two equations to happen simultaneously. Because whenever this happens, then you must have what? X equal to 0. You must have x equal to 0. Because you can, it seems the left hand side are equal, these two sides must be equal. I hope it's okay. But then x is not 0 because you are picking a different element of the semigroup. Is that okay? So you always must reach a conclusion that every other thing in the semigroup must be 0. So the only situation where you have the identity equal to 0 is when the only element in the semigroup is 0. I hope it's okay. So if equality happens, if there is at least 2 elements, then identity cannot be 0 because this will happen. So but we don't want to call, now in this situation, this element is both 0 and identity. So which one do we call it? Because if you have a semigroup where identity and 0 are equal, that semigroup must be true. It must contain only one element. Let's say E. only one element, because the element must always be, every element you take x must be 0, to be that same 0. So so that element 0, we don't want to call it 0 element. That is, if you have a semigroup or with only one element, you don't want to call the element 0. You want to call it identity. I hope it's okay. You want that element to be called identity. And so therefore, that is why in defining a semigroup with 0, we say it must have at least 2 elements. So that if you discover a 0 existing, whereas the semigroup is only consisting of one element, then that 0 is not called 0, but what? The identity. Because it will behave like identity, it will also behave like 0. So that is the reason why we must say, for 0 to exist, the semigroup should contain at least 2 elements. So this is this one now. Now, so that's one remark I made. Now I was talking about group. Okay, you say, can a group have more than 2 elements? Is it possible to a group to have more than 2 elements? No, not more than 2 elements. Is it possible for a group to contain 0 element? I think you answered that question, Go. You said no, because if it has identity, it will have a Vasco. Uh, we have other examples of semigroup. We can have a semigroup. If you give me semigroup with 0, if you give me a semigroup, any sets, you give me any sets with any number of elements. So on any set, maybe I should present it as a definition. A semigroup, a semigroup with 0 is called, S with 0 is called a 0, a null semigroup. Null semigroup. If for all xy in the semigroup, x times y equal to 0. That is when anytime you multiply in the semigroup, you get 0. The product of any 2 elements in the semigroup is always 0. Then it's called a null semigroup. So everything is crashing down to 0. I hope it's okay. And then I can still define an element to be called a left 0, because you can have situations where you don't have 0 element, but there are left 0 and right 0. That is element for which anytime you multiply with them from the left, you get the element back. Okay, so an element A in a semigroup S is called left 0 if for all x in the semigroup Ax is equal to A. Then you say the element is left 0. The element A is left 0 element. And similarly, an element B will be called right 0 if what? Anytime you multiply with it from the right, you get the element back. An element B in a semigroup S is called right 0, element if for all x in S, x times B is equal to B. So called right 0 element. These concepts are not difficult. Very. Sure. So I don't know that you can think in this way. If you have a const, like you are think of mappings. You see, if you look at the collection, I'm going to talk about it later on. But let me just say, uh, just to give you a feeling that you can have this situation in a semigroup. You see, if you are looking at the collection of all maps, you remember permutation symmetry group? These are one-to-one and onto mappings of a set X. So, but if you have a set X, all mappings from X to X, take any two such mappings, you can compose them. The composition of the mapping is still a mapping from X to X. And composition of map is associative, we know this. I hope it's okay. So the collection of all mappings with composition of mapping will give you a semigroup. It's an example of semigroup. You know, this will be our very good candidate, the semigroup we will be dealing with most of the time. The full transformation semigroup of mappings. Are you following? So if this thing, the composition here is a binary operation of composition, and these things are mappings. So if you are living in dealing with a semi-group of mappings, and then you think of a map F composed with another map G, and this G happen to be a constant mapping. Whatever F is, anytime if you compose, this is a constant mapping. So at the end of the day, you get everything mapping to that image. You will always get G. So anytime you compose with constant mapping from the right, if F acts on the element, G will always act on it to map it to the constant number, the image, and you always get what? G. So for a constant mapping, every constant mapping is a right identity. Are you following? If you are inside the semi-group of mappings, I hope it's okay. So how many such constant mappings do you have? You will have up to the size of the set, the domain and the codomain, the set you are transforming. I hope it's okay. So which means this notion of right 0 and left 0, this is not unique. You can have so many left 0 elements in a semigroup and so many right 0 elements in a semigroup. So many. I hope you are following. So it's not like the situation of 0 elements. In the situation of 0 element, if it exists, it must be unique. But here you can have so many of them. You know, at least you can see many here. So let me define left 0 and right 0 semigroup. So a semigroup S is called a left 0 semigroup if all elements of S are left 0. If every element of S is a left 0. You say every element of S is a left 0, it means for all, so that is for all x, y in the semigroup, the product of x, y is always x. Whenever you multiply, you get the leftmost element. So if the product is defined in this way, then the semigroup is left 0. Semigroup in its entirety. Every element is a left 0. I hope it's okay. We will encounter semigroup like this, where the product is always giving us the leftmost element of the semigroup. And the right 0 semigroup is defined, right 0 semigroup is defined similarly. That is, anytime you multiply, you get the rightmost element, a right 0 semigroup. I hope it's okay. Okay? Alright. So, do we still have time? Hmm?
1 hour.
Okay, so I think we stop here. It's a good point to stop. In the next class, we are going to look at, so we will just continue defining these basic concepts, basic definitions. I think this is where we stop today. Thank you very much.